So yesterday we talked about a dark matter candidate that's different compared to the ones of the previous two lectures. So an extremely light particle that's produced coherently at some point in the history of the universe, and then the energy density, the dark matter energy density, it's encoded in its oscillations around the minimum. And for us, this was a generic scalar yesterday, but today we're going to talk about another mystery in the standard model Lagrangian, which is the value of the electric dipole moment of the neutron, how this mystery could be explained by a particle similar to the one we've seen at the end of yesterday's lecture, and so how this particle could at the same time be dark matter and explain this other puzzle that we face today in fundamental physics. And so we're going to change gears a little bit, so not talk about dark matter today, but start talking about the Lagrangian of strong interactions. So this Lagrangian contains a term that we can write like this. So I think I've already told you what I mean by GG dual in the first lecture, but I'll repeat it. So this operator is the antisymmetric contraction of two gluon field strengths. And one can check that under the CP symmetry, this object is odd. All other terms in the QCD Lagrangian are even if the quark masses are real. So you can write the rest of the Lagrangian like this. Where again, I'm imagining to trace over the color indices. So if you want to be pedantic, this is what I'm looking at. And well, it's convenient to write explicitly the quark mass term in this way, so to see that if it's real, there is no problem with CP. So, well, and here I'm imagining to sum over all different quark flavors. So in the limit in which the quark masses go to 0, this theory preserves CP. And so you expect, if this term has no effect, to see CP invariant spectra of hadrons, so all low energy predictions of QCD to be CP invariant to very good accuracy. However, well, we know that weak interactions violate CP at order 1. And we will see in a second why it's surprising if strong interactions don't. So imagine that you were to find that this parameter is very small, so that strong interactions approximately conserve CP, or maybe not that parameter, but the observable one. So the combination of that and an appropriate sum of phases of the quark mass matrix that we're going to see in a second. So if the relevant parameter for which QCD breaks CP was tiny, that would be surprising. And we will see why in a second before better defining this parameter. And so we will start the lecture by understanding better why this would be surprising. And then we will introduce this particle that makes theta dynamical. So you've seen anticipation of this fact a few times already. And I'm sure that some of you are familiar with what I'm going to say today, but I'm going to add some details that are often overlooked or taken for granted, which is never a good thing. So the first question that you might ask is whether this theta parameter is observable at all or not. And to better understand whether it is or not, we can take a step back and reconsider symmetries in quantum field theory. So let's say you have any symmetry transformation of the quarks. Which leaves the action invariant. So this is not yet enough to call this a symmetry of a quantum field theory, because as you know, the measure in the path integral might change. So if you're actually applying this symmetry transformation, you can ask how the integration measure of the path integral changes. And OK, with minimal effort, you can find that, well, not so minimal, but minimal if you've already seen the quantum field theory course that I'm sure you've seen. You can conclude that the measure changes in this way. So if your transformation is unitary, then, well, you have no problem. These two factors of the determinant give you unity, and the measure of integration remains invariant. So that is why most of the time you don't even consider this point. So once you find a symmetry that leaves the action invariant, you consider yourself satisfied and start working out the consequences of this symmetry. However, let's imagine that we choose as our U operator this object, where this T is some generator that we're not necessarily going to specify that can act on the quarks. Then, well, in this case, well, you will find that the determinant of U bar is actually the same as that of U. So your path integral measure is going to change. And we can always use a general property of matrices, which carries on to some extent also to infinite dimensional operators, to write this change of the measure as a change in the action. So in particular, I'm going to use this identity. So you can rephrase the shift of the integration measure as a shift of the action, which is going to itself to -2 of the trace of this log, okay? This is just to give you an idea of a classic result, which I'm not going to prove, which is that if I do this change of variables in my path integral, sorry, this change of variables in my path integral, where in principle this parameter alpha can be different for each one of the quarks, then this is going to cause a shift in the Lagrangian density by this amount. So since this transformation is clearly not a symmetry of our theory because it's changing the integration measure, or if you want, it's changing the Lagrangian, then what we've done is not a symmetry transformation. What we've done is a change of integration variables in the path integral. And so observables cannot depend on how you choose to parameterize your field variables. So the only objects that you can measure are those that are left invariant by this operation. And in particular, you see immediately that theta, so the parameter that we started looking at, is not invariant. So under this reparametrization, theta is going to shift. So I'm going to look it in the notes because I don't want to mess up the sign, but it's going to shift by this amount. So theta alone is not observable, but okay, if you do this transformation, you can see immediately from the way we've written the quark mass matrices that also the quark masses are going to shift. In particular, we're going to get this. So interestingly, the determinant of the quark mass matrix, so if we look at the phase of the determinant of the quark mass matrix, this guy transforms in the opposite way as theta. So if we combine these two parameters, we can easily construct an object that is invariant under this change of integration variables, and as a consequence, in principle, can be measured. So this is the quantity that controls CP violation in strong interactions. And you see now also why it's surprising that it's small, because quarks talk also to weak interactions. And so the moment you extend the standard model, you expect the CP violation, that it's order 1 in weak interactions, to be communicated also to this parameter. Right in the standard model, this doesn't happen due to a numerical coincidence that in part you see also here. Since you need to go through all quarks, in the end, the object multiplying the phase that enters CP violation is small. It's called the Yarsklov invariant. Actually, Christophe mentioned it yesterday during the colloquium. And so numerically, it's not weird in the standard model that this parameter is small. You start finding something surprising the moment you extend the standard model. So if you want, this is very similar to the mystery surrounding the Higgs mass or even the cosmological constant. So within the standard model, well, it's not exactly the same, but within the standard model, the Higgs mass is not calculable. Using only symmetry, you expect it to be of order the top mass, and in fact, it's not that far away from it. But the moment you extend the theory, then again, using just symmetry, you expect it to be much bigger than what we observed. And here, it's the same, okay? So I'm not going to do the calculation explicitly for you, but if you extend the standard model, you expect order 1 contributions to theta if you do it naively, so in the simplest possible way. And so we want to explain, at the end of this lecture, we will want to explain why this parameter is small. But before that, I think it's instructive to ask how we could possibly measure it. And the first thing to notice is that there would be no surprise if this parameter was 0 if one of the quark masses was 0. Because let me say that, I don't know, the mass of the up quark is 0. Then I can always choose my alphas here in such a way that the up quark changes by this amount, and no one else does. So essentially, I'm taking alpha up to be theta over 2 minus theta over 2, and I'm taking all the other alphas to be 0. Well, if I do that, obviously, I'm setting theta to 0. So theta goes to theta minus theta. But nothing else is happening because so the product of these quark masses is 0. Or if you want, more simply, if you just look at the Lagrangian, if one of the masses is 0 and you shift the quark whose mass is 0 by that amount, you're going to have a transformation only on the kinetic term, which is invariant. Actually, here I dropped gamma mu. So this is the simplest explanation for why this parameter could be small. So if one quark mass is 0, this parameter is just unobservable. But before getting to the puzzle itself, let's see if this parameter has any physical consequence in the standard model, any measurable one at least. So we've seen that in principle it is measurable, but we don't know yet how we can measure it and whether we can get any decent accuracy on its determination. So here comes the hard but also interesting part, because, well, most precise measurements of QCD that we can make are at low energy, so below the scale at which QCD confines and becomes strongly coupled. So we cannot use this Lagrangian as it is to make predictions. At least we don't have the computing power to do that yet, except for a few observables. And so we would like an effective description of the degrees of freedom of QCD at low energy that allows us to make some prediction and see if this parameter is measurable or not. And well, the first step for any of these efforts is to identify the symmetries of this Lagrangian. So there is clearly a U1 symmetry that I'm going to call vectorial, which corresponds to changing the phases of the quarks. So if you do this transformation, you can just notice by looking at the Lagrangian that it's invariant. If you take the quark masses to be 0, so now we're starting to talk about approximate symmetries, then you have a much bigger symmetry, because any SUN rotation in this n flavor space leaves the Lagrangian invariant, right? So any unitary transformation of this kinetic term doesn't do anything to our theory. So if the quark mass is at 0, we have also an SU3 vectorial times an SU3 axial. Or if you want more simply, you can call it left and right, because we can write the kinetic term as a sum over left-handed and right-handed spinors. And we can rotate the right-handed and the left-handed guys independently, so each one of these is a symmetry of the theory. We have just seen that the companion of this symmetry with a gamma 5 here is not a symmetry of the theory, so we cannot add this U1A factor. Note that, well, this symmetry actually would be realized even if the quark masses were non-zero, but all the same. So say if m up was equal to m down, etc., etc. So what's breaking this symmetry are really the differences in quark masses. At least what's breaking the vectorial part of this symmetry. Okay, so the vectorial part of this symmetry is broken by the differences of the quark masses. If you want the full group, then okay, you need the masses to be 0. So okay, this is the first step. So identifying the symmetries. The second step is to understand the vacuum structure of QCD at low energy. So at low energy, the quarks get a vacuum expectation value. Actually, I should call this vacuum state omega, because it's an interacting vacuum. And so this is the dynamical scale that characterizes QCD. And we're going to be more precise about it in a second. Before that, let me tell you what this vacuum structure is teaching us. So what this vacuum structure is teaching us is that so there is a collection of degenerate vacua, because let's make a transformation of this symmetry group. So we can write the quark bilinear like this. So under a transformation of that symmetry group, it's going to go to this, and I'm not going to write the second term because it's obvious what it's going to look like, and I've called L an element of SU3 left and R an element of SU3 right. So you see that if I choose the transformation so that they have the same parameter, so I limit myself to the diagonal subgroup, the vacuum structure remains invariant, because this will just give you unity if the parameter of the left and the right transformations are the same, so that L dagger is equal to R dagger. But if they're not, then this vacuum is going to shift. Yes? Sorry? L dagger, no, that's fine. So L dagger, what do you mean? So this is, I want the same parameters of the transformation. Yeah. Anything else? No. Okay. Okay. So so essentially, what we're looking at is a theory where we have a non-trivial vacuum structure. Okay, so the theory still respects the full symmetry group, and I'm still talking in the limit of 0 quark masses, which means that when these two transformations are not the same, you're moving around between vacua with the same energy. Okay, so there is a transformation that leaves you in the exact same vacuum, which is the one where the two parameters are the same, which we're going to call SU3V. And then there is a transformation which is moving you between degenerate vacua, which we're going to call SU3A. Okay? Well, you've seen this probably a million times in courses talking about spontaneous symmetry breaking, but well, maybe I will not be the first one telling you this, but spontaneous symmetry breaking is a terrible way to put it, because nothing is broken here. All that's happening is that you have some flat directions in the potential, and one of your symmetries is moving you around these flat directions. And so immediately you expect that there are massless particles, because the mass of a particle is the second derivative of the potential. So if there are some directions where this derivative is 0, well, obviously you are going to get massless particles. And well, there's a beautiful general result by Coleman, Callan, West, and Zumino that allows you, given a symmetry structure of your theory, to parameterize this massless degrees of freedom, right? So by just staring at this blackboard, you don't know how to write down in terms of the quark fields, the massless fields, okay? You know. But it turns out that you can guess, well, actually not guess, but compute precisely what these massless fields look like using only symmetry. And so, well, this is a relatively involved story if you read it in some references, and so even if it's well known, I wanted to give you my simplified version. So we're going to call the generators that leave the vacuum invariant T. And so for us, these are the generators of SU3 vectorial. Okay, but for a moment, we're going to do things more generally. And then we're going to call X the generators that move you somewhere else. Okay, so in another vacuum of equal energy, but which is not the original one. Then, okay, it's a general group theory result that the most general group element, so now I'm going to call G the full symmetry group, so the one given by the two factors of SU3, can always, so this group element G can always be written in the following way. So this is not trivial because the generators X and the generators T do not commute. So the product of the two exponentials is not equal to the exponential of the sum of the arguments. However, this is true. Okay? The second, so this is just a mathematical fact about group theory. The second, obvious mathematical fact is that if you multiply a group element by another group element, then you still have a group element. So this is still in the group. Okay? So I've chosen an element of the group which is spanned only by these X generators, but this is still an element of the group like everyone else. And so now, well, I can use the trick number 1 to write my group element at point 2 as a product. So, and okay, this might look unnecessarily complicated, but everything that I've written on the blackboard has a reason to be there. So first of all, the indices of the X's and of the T's are different because in principle they can span completely different numbers, okay? It's a coincidence that we're looking at two symmetry groups that are the same for the T's and the X's. Here, I've written that theta prime and Xi prime depend on the factors on the left to highlight the fact that, we have something nonlinear. So for sure, we can write any group element in this way. But in general, the relation between these parameters and the original parameters of the group element is not going to be a simple linear relation. I cannot promise you that. But you see, essentially, with almost no effort, I found how these objects transform. Because now I can just multiply everything by the inverse here. And I know how this object transforms under a group transformation. So this is the transformed element, which is equal to the original one times the group transformation times the inverse of this guy that I'm going to call H. So this is H to the minus 1. So why did I do this? So I did this because this simple equation is already telling you where to look for the massless guys, right? So the massless guys in your theory are those that are parameterizing the flat directions of the potential. But the flat directions of the potentials are those that connect different vacua. So my massless fields are going to be in the direction of these generators. And this is, in some sense, purely intuitive. Of course, you can prove all this stuff that I'm telling you rigorously, but the point that I want to make here is that there are very simple intuitive explanations. I'm sure you've already seen Goldstone theorems spelled out in a million different ways. And so, okay, so once I made this realization, then I can very well try to write down my massless fields exactly in this way. So I want something in the directions of the generators. And, OK, I'm going to just tell you that I want to parameterize them in this way. And the reason that I want to parameterize them in this way is because I can derive this very simple transformation law under the group. OK? Because to work with these objects, I want something that I know how it will transform under the group, so that I can construct an effective Lagrangian that matches the symmetries of the energy ones. So if you want the logic, if you want me to break it down once more, is that I know that massless fields needs to live in these directions, and I know how to play with exponentials of generators. So I'm going to start by trying to parameterize these massless fields this way, so that the thetas are the massless fields. And if I do it, I can indeed derive a simple transformation rule for these objects. Now, this transformation rule is relatively simple, but you see that it's non-linear, so it depends on your fields and your group transformation in non-trivial ways. So it's not immediately simple to construct a Lagrangian once you have this object, because, for example, when you take derivatives, they're going to act non-trivially on the transformation matrices, so on this H, for example. So it's a bit a similar problem as when you try to construct a gauge theory. And, well, so in general, Coleman, Callan, West, and Zumino found a very simple way to split this object into other objects that transform linearly under the group. But, well, I'm not going to tell you how, so unless you ask, but it's a beautiful general result. However, in our case, there is an important simplification that can be made. So since our group is this SU3 left times SU3 right, you can immediately notice that there is a transformation that leaves the group invariant. So if you send the generators of the axial part to minus themselves and to the vector part to themselves, then essentially you're just flipping left with right. So since your group was left times right, right times left is the same thing. And in this case, it's very convenient to work with this object, where Xi is defined as our initial initial matrix of massless fields. And this Xi tilde dagger, Xi tilde is what you get from Xi once you apply this transformation. So let me call this transformation A. So if you apply the transformation to Xi, you're going to get Xi tilde. And well, given the structure of the group that we're dealing with, for us, Xi and Xi tilde dagger are the same. So in the end, U is just e to the 2i theta x. OK? So this might look like something stupid. So I started with this guy, and now I'm just looking at this guy squared. But the nice thing about this guy squared is that you can see immediately from this equation that tells you the transformation properties of one of the two guys that now U transforms linearly. So apply this transformation to U. What you're going to get is that U goes to G, U, G tilde, where again G tilde is G to which you applied this transformation. Okay? And now this factor of G was just the original group transformation that you've chosen. So it doesn't depend on your parameter theta, it doesn't depend on anything, it's just a matrix of numbers, whatever transformation you chose to do in the first place. And so now you have an object that transforms linearly under the group, and we can apply this general construction to our specific case. So this was a bit abstract, so if you have questions, good. Great timing, yes.
Why decide that, or did the sign just square the one side of it?
Yeah, because, so this guy, so okay, because the transformation is x going to minus x, psi is e to the I theta x, and so psi tilde is e to the minus I theta x, and psi tilde dagger is e to the I theta x, because we are looking at Hermitian generators. Okay. No. Anything else? So I made an effort to make this simpler than it's usually. I mean, than the way it's usually presented, but I might have also obtained the opposite result. So if you're confused, don't feel embarrassed. You can ask me. Yes?
Why are we doing this? Because you broke the symmetry, right?
Yeah, I didn't break it.
Okay. But why are you trying to rewrite these guys?
Yeah, because essentially what we want to do is to write a Lagrangian with which we can make predictions at low energy. Okay, so this Lagrangian is strongly coupled at low energy, so we don't know how to use it. And the most relevant objects at low energies are massless fields. So we're starting to construct the Lagrangian for the massless fields. And there is this very general formalism that allows you to identify the massless fields. So that's the logic. No problem. Yes. What G tilde? Ah, yes. G tilde is G to which you apply this transformation. So you send the generators that leave the vacuum invariant to themselves, and you send the generators that change the vacuum to another vacuum to minus themselves. So say if G was a left-handed guy, so if G was an element of SU3 left, G tilde is SU3 right. Okay, so at this point, any more questions? No. Yes.
That's a short one. So what we have written as second condition is that this one compensate the exploitation value is non-zero.
Mm-hmm.
Just we have seen this experimentally. There's no like hard theory way to derive it.
Yes, yes. So I'm not sure whether you can even say you probably can see it theoretically, but historically, yeah, the path is that we found it experimentally, even though indirectly. Let me see. Let me think for a second, because well, for GG dual, for GG, you can relate this vacuum expectation value to the trace of the stress tensor and some anomaly, but yeah, I mean, as far as I know, we cannot compute this object from first principles yet. I mean, unless we do it on the lattice. Okay, so now we are looking for this U in our let's say QCD theory. Okay, and so we know that the different vacua are essentially so we are looking, so this is the object that has a non-zero vacuum expectation value. And so essentially what we're trying to do with this U is to parameterize all the vacua, right? So we are looking at the directions in the potential that are flat. So this U should have the same transformation properties as this object for obvious reasons, right? So if a transformation is leaving the vacuum invariant, U must also remain invariant. If you're moving along this flat direction, then U must also move. And so this object, for example, well, so we've broken it down, so we can decide whether we want to call U this guy or this guy. It's just a definition. So if we call U this will be U dagger, and vice versa. So let's say that we choose the conventions in which U transforms like this object. So U now is a 3-bar 3 of SU3 left, SU3 right. So let's say that we want to know how it transforms under a group transformation, and we choose, say, G to be an element of SU3 left. So in this case, well, we have a L dagger because this is a 3-bar, and then we know that from, well, we know both from this equation and its transformation properties that it will go like this on the other side, right? So essentially we have chosen a group element and then used this transformation property that we derived in general. So, yes?
G is the SU group SU3 left?
Well, this was just an example. So in general, U will transform this way, because let's say you choose an element of SU3 right now. Then, okay, you know that U transforms this way on the right because of its transformation properties, and then you know that you have to put an L dagger on the left because of the general transformation property. So we made all this effort just to get to this. So now we have an object that parameterizes our massless fields, and we know its transformation properties. So we can construct a low-energy Lagrangian that respects all the symmetry of our high-energy theory and see what we can get from there. And well, that's a relatively easy task, at least at the order that we are interested in. So this low-energy effective Lagrangian that I'm going to call the chiral Lagrangian, well, needs to have a kinetic term for these objects. But OK, it's pretty easy to convince yourselves that this term is invariant under an SU2 left times SU2 right transformation. So you can see it immediately if you apply it. To get the right dimensions, we need an object with the dimensions of a web in front. So I'm just going to put this parameter. I'm going to call it f pi for the moment with no explanation. Okay? This is just dimensional analysis as far as we know now. However, okay, we know that if we turn on the quark masses, this symmetry is broken. So there must be a term that reflects this breaking by the quark masses. However, it's broken in a very specific way, because let's say that I put the quark masses in a matrix. Then I can ask myself, so let's say that I want to restore the symmetry by promoting M to a field. How does M have to transform to restore the symmetry in the high energy theory? Well, and the answer, well, it's very simple. So it has to transform in this way. Or maybe actually I've been, well, I think I've I've inverted my definitions, one compared to the, no, okay, actually that's to transform this way. I was coherent with my definitions. And that you can see it from the high energy theory, right? So if you transform these quarks, and well, it's reflected in my choice of what I call them Q and what I call them Q conjugate. So if M was a field, this transformation property would restore the symmetry. And so I can use this fictitious symmetry property of M to construct the term at low energy that it's actually breaking the symmetry, but it's breaking it exactly in the right way. And this term is this. And well, okay, it's immediately evident from the transformation properties of M and U that if M actually transformed, this term would preserve the full symmetry. But since M is a collection of numbers and not a field and is not transforming, it's breaking the symmetry exactly in the right way. So now I want to make another digression, and you might hate me for that, but some of you, I think, one day in the future will thank me for that, for the following reason. So why do you think I wrote lambda and f pi squared? So why 2 scales and not just another f pi cube? So we, what do you mean? Fine-tuning, you said? No, there is no fine-tuning here yet. It's very simple, okay? So we are used to work in natural units, but objects have dimensions, okay? Natural units are just a simple way to book, they're just a way to make our life easier, okay? So do you want to try after this suggestion to guess why I wrote 2 different numbers? Okay, if not, I will tell you. So if you restore dimensions to H slash, couplings have dimensions, and so masses and webs have different dimensions. Okay, so a mass is a gauge coupling times a web. The coupling has dimensions of square root of H slash. Okay, and actually this is a fantastic way to keep track of couplings, factors of pi, webs and masses in strongly coupled theories. Well, it's known at, okay, it's probably been known almost forever. Probably the first people using it in a sociologically successful way were Georgai and Manoir in their NDA paper. But, okay. So this means that I have to be careful when I write down a Lagrangian, for example, of whether I'm putting the right powers of masses and webs. Okay, so if you ask what are the dimensions of a Lagrangian density, you can convince yourself as an exercise that this has dimension mass squared times web squared. Okay, so here I already have a mass and a web squared, so I need another mass. The interesting fact about QCD is that it has only 1 scale. And I'll tell you in a second why. So at least when you set the quark masses to 0. It has only 1 scale. So in reality, these lambda and f pi are not, okay, so if I was just at low energy, if I knew nothing about QCD, these would be 2 independent numbers, okay? They would maybe be related by a coupling, but I wouldn't even be sure of that. But I know that in QCD there is only 1 scale, so these 2 guys must be related by a coupling. And experimentally, it's roughly 4 pi. So this lambda is roughly 4 pi bigger than f pi. But OK, for now, this is the mini digression. Now let me make the bigger digression. That, however, I think it's illuminating for a series of reasons, because it also allows you to think about a whole class of solutions to the hierarchy problem in a more precise way that sometimes is obscured. So what do I mean when I say that QCD has only 1 scale? So okay, we can look at the Lagrangian. We can even add our friend theta. Okay, and the action, okay, is going to be just the usual space-time integral of the Lagrangian. Okay, so now let me again set the quark masses to 0. And I'm doing this all the time because of the experimental fact that we know that the QCD scale is much bigger than the quark masses. So it's a small mistake, so the light quark masses at least. So, and the heavy ones, it's something that you can integrate out. So let me maybe be a bit more precise about this point, or I will confuse you a lot. So let me just, for now, set the quark masses to 0 with no justification. Okay? If I do that, then I can do a scale transformation. So I'm just going to rescale all my coordinates by some amount. What happens if I do that? Well, if I do that and the quark masses are 0, this action remains invariant. So this factor is going to get an s to the 4. But all these operators, except the quark masses, are dimension 4. So they're going to get an s to the minus 4. So I have dimension 4 in energy. Okay? So at the classical level, QCD without quark masses is scale invariant. So it has no scale at all. However, well, we know that, quantum corrections break the scale invariance, right? So the QCD coupling is running. So if the theory was exactly scale invariant, the QCD coupling would be the same at all energies. But this is not the case. And the picture, so that I'm going to have in mind, which is consistent with what we know of QCD, is that at some large energy scale, the coupling is very small. Okay? This is consistent with the running of QCD that we know of. So I can imagine that after this scale, the theory is exactly scale invariant at the quantum level. So there is some scale where this coupling is really 0. Above, the theory is exactly scale invariant. Below, okay, I have to run the QCD coupling. And I'm going to get the following. So what I'm going to get is that this coupling is running logarithmically, and the scale lambda at which it becomes strong, so let's say infinite or more than 4 pi, can naturally be exponentially smaller than this large UV scale. The reason is that is what I told you before, so that we have only marginal operators. So things are changing very, very slowly as a function of energy, so they're changing logarithmically. And this makes natural a big hierarchy of scales. And going back, so this is a general comment that might be interesting to you independent of what we were saying. But going back to what we were saying, you see that this, well, is the only scale that we can talk about in this theory. Okay? Everything is marginal, and the only scale that appears is generated dynamically by running. And so this f pi and this lambda somehow have to have the same origin and be related to this scale. And indeed, so as I was telling you before, this lambda here is what you get from the running, and f pi is roughly a factor of 4 pi below. Now, you might say, OK, well, this is all very nice, but you know that quark masses are non-zero. Actually, some of them are even big compared to this scale. So why the top mass doesn't spoil completely this picture and introduces a new scale that is much bigger than this one? And the answer, well, is not totally trivial. The answer is chiral symmetry. So essentially, well, it's what we said before. So if you turn the masses if you set the masses to 0, a big symmetry appears, left times right. If you turn them on, this is broken to the diagonal subgroup, where you choose the same parameter of the transformation for left and right. And so, as a consequence of this symmetry, you can repeat some Spurian analysis as we did here. And so you can ask yourself, how do the quark masses run? So, sorry, as a function of energy. So you can write the RG equation for the quark masses. And as a consequence of this symmetry, so only quantities that break this symmetry, exactly like the quark masses, can appear on this other side. So in practice, you're going to find that you have to add in the running, so in front of everything, a factor of MQ, whatever you had at 3 levels, so the original parameter that was breaking this symmetry. Because if you apply this symmetry on this side, you're going to get the usual, right? Oh, sorry, I wrote it backwards. And so clearly also the right-hand side has to transform in the same way. So this is actually another general point. So it's showing you that broken symmetries are often more powerful than exact symmetries in quantum field theory because they give you selection rules. And so, well, the only object that we have in our theory that transforms like this is the quark mass itself at 3 level. So on this side, you can only have the same scale that you already had. So you cannot have any power of energy or anything else. So now by dimensional analysis, you know that everything inside the parentheses is dimensionless. And so the best you can do, so the fastest you can run with energy is with a log. And so even if the quark mass operator, so this object here has dimension 3, as a consequence of the chiral symmetry, is running like a marginal operator. So effectively, it's not spoiling our QCD scale, approximate scale invariant story because of this fact. Okay, so this was a big digression, but there were a lot of gold coins hidden in this argument. So if at least one of them will be useful to you in the future, I think, well, I did my job. Okay, so, yes?
Just to back up, you can't be exactly scale invariant above some point, right? Because if alpha also is actually 0 at some point, it will stay 0 forever. It can be arbitrarily small, right? But it cannot be definitely 0.
Yeah, sorry, you're right. I mean, all that matters is that alpha strong remains the same above the scale. So it's not running anymore, and everything is scale invariant.
No, that's what I mean. It is running. It changes the negligible amount.
Wait, so above the scale, so where the theory is really scale invariant, it cannot change. I mean, it cannot change because otherwise the theory is not scale invariant. But you don't need it to be 0 here. That's true.
No, but this is the point. If it's exactly scale invariant, how can this break dynamic? It has to be.
So the breaking comes from the fact that, okay, maybe I didn't understand what you're confused about. So are you confused about having alpha 0 at this scale?
If a theory is exactly scale invariant, it cannot be broken because the breaking is at some scale, but the theory is scale invariant. So the scale cannot be
well, okay, I see, yes.
Exactly scale invariant.
Well, let's see. So I see your point, but it's not true that, for example, a conformal symmetry in the UV cannot be broken. Well, yeah, okay, yes. In some sense, philosophically, you're right, but in practice, in practice, the way it works is that you're going to have some relevant or irrelevant deformations of this theory. Well, with relevant is easier. So let's say you have a small mass that is of order lambda UV, okay? If your at energy is much larger than lambda UV, the theory is scale invariant because the effects of this mass are going to be suppressed by the mass over the scale. So, yes. I guess, yes. Yeah. Anyone else?
We wanted to argue when we look
No, so mtop, yeah, the running of mtop itself, yes, but it's running slowly, so it's running logarithmically. So what mtop is not spoiling is the argument that everything is running slowly between the UV scale and the low energy scale. So it's not spoiling the fact that you can have a big hierarchy. In practice, mtop is not, well, and the other thing that it's not doing, that mtop is not doing wrong, let's say, is that it's not entering as any power law correction to this running. So mtop will be a threshold on this running, so it's changing the order 1 factor in front of the logarithm in the running, but that's all it's doing, right? So above mtop, this numerical factor will be a bit different than below mtop.
The second thing is like the breaking scale, as Shakib said. I mean, alpha S goes asymptotically to 0, but never is exactly 0. So we say what is like the smallest error we can take, and above that we say it's approximately scale invariant.
No, but
it's not, but that's like a choice.
Yeah, no, I mean, I corrected myself. You don't care for, I mean, even if the coupling is not 0, the theory can be scale invariant. Okay, it doesn't even need to be small. All that you care about is that it's not changing anymore as a function of energy up here. So for example, well, also your colleague talked about interacting fixed points. So you can have theories that are scale invariant or conformal and have large couplings, but only these couplings are not changing as a function of the energy scale. Okay, so it's not crucial that the coupling be small for the theory to be scale invariant. Yes.
What you do change, just you don't care about it. You have to change.
So okay, if you okay here, yeah. So if you talk about the real world, fine. Okay, we philosophically agree. But if now you take a conformal theory.
It's mathematically, if you're at a fixed point, you're going to stay at a fixed point. Right?
Yeah, exactly.
If you're close, you can flow.
Sure, but yeah, but okay, that's established, I think. Yeah, I forgot what was your question. So I mean, I thought that this was not applying to what we were really saying. So, what was your question again?
How we can say it's scale invariant when there's still a running, although it's maybe small in Qcd.
Ah, no, okay.
Fairly small, but it never goes exactly to 0.
Oh, okay, no, but you don't have to necessarily just take Qcd as it is above the scale, right? So above the scale, all sorts of things can happen. So you can have new matter, etc., etc.
Like matching to some bigger model, and there we
Yes, exactly. So here you can have a bunch of other stuff that are making the coupling flow to the fixed point, for example. Yes.
I got a bit confused there with the dimensional analysis.
Yes.
So could you repeat a bit once again? Because
Yeah, so if you don't set h/ to 1, then okay, you can repeat the usual steps, right? So if you set h/ to 1, you can deduce from the fact that the action is dimensionless what are the energy dimensions of the operator, okay? But now you're not setting h/ to 1, and so some objects that were dimensionless in natural units become dimensionful. And you can see, I mean, it's easy to see as an exercise that gauge couplings have dimensions, of 1 over square root of h/. Okay? And in the same way, you can see that masses and webs do not have the same dimension, but are related by a coupling. So they differ by 1 over square root of h/. It's very simple. Okay, so I think this digression interested you so much that I said much less than I wanted to say. But yeah, so now we are back here, which was our starting point all along. And now, so well, you might so you have to wonder about something, because the theory that we started with, the one with theta, is breaking the U1 axial symmetry in two distinct ways. So if I call the U1 axial symmetry this shift that I was talking about, then, okay, if you do this shift, as we've seen at the beginning of the lecture, the masses are shifting, but also theta is shifting. Okay? And in this theory, we're breaking the axial symmetry only in this term. Okay? So an axial transformation here would look like U goes to e to the I alpha, e to the I alpha. So you can work it out as an exercise. And so, okay, you can see that this term breaks it, but this term preserves it. So somehow we're missing something. So we have to add, so if we want to reproduce the effect of theta, we have to add to this Lagrangian another term that breaks explicitly this U1 alpha. And if you try, you will find that the only one that does it is this one. So you're looking for a function of U that preserves all the other symmetry but breaks only U1A. And you can try, and you will see that this is the only option. So how much time do I have left?
25.
Ah, okay, so quite a bit still. Okay, good. Okay, so now we have our Lagrangian. And we can start figuring out what theta is doing at low energy. So what observables it's entering and what's going on with it. Okay, so let's imagine that in the original theory, so in the UV, we have changed integration variables in such a way that we eliminate this term and move all of theta in the quark mass matrix. Okay? This makes our life easier at low energy. So we can simply write the mass matrix including theta. And for simplicity, for the next 25 minutes or however long we have, I'm going to work in QCD with two flavors. So I'm going to consider only the up and down quark. So the heavy quarks can be integrated out, and they give you only small corrections proportional to some power of lambda QCD over the quark mass at low energy. The strange has a mass comparable to lambda QCD, so you're making an order 1 mistake by integrating it out, but the physics does not change qualitatively. So I will give you this derivation in a two-flavor setting, which is much easier to understand intuitively. Okay, so now we have our quark mass matrix, and we can also write our fields explicitly. And so since we're dealing with two flavors, we're in SU2 times SU2. So the broken generators are those, I tried to avoid saying broken, but the generators that do not leave the vacuum invariant are those of SU2, so Pauli matrices, plus potentially, okay, this U1A object that we need to determine what's going to happen to it. So now, yes. The what? Q. No, there is eta, F, eta, yeah, eta. This is eta. So this is a field associated to that U1A transformation. A priori, okay, since the transformation is broken, we might expect it to be heavy, but let's see what happens. So let's see what we get at low energy. So we don't know yet if this is to be considered within the together with the massless guys or not, because these generators here that do not leave the vacuum invariant and are associated to the pions are explicitly broken only by the quark mass matrix. So we already know that these particles will get a mass proportional to the quark masses, so potentially much smaller than the dynamical scale of QCD. In the case of this other boson, so eta, we don't know yet because we are sure that the quark masses are breaking the symmetry. We've seen it explicitly. We're also sure that this term is breaking the symmetry, but from high energy perspective, we don't know yet if this term is really doing anything, because we can always write it as a total derivative. And later on, I'm going to tell you the explicit expression for K, but you can also try yourself as an exercise. So a priori, we don't know what's going to happen. So maybe this eta particle is going to be one of the light ones. And in reality, we are worrying about this theta for nothing, because this is a total derivative. So if you integrate it over space-time to get something physical like the action, you're going to get that if fields die fast enough at infinity, this term will not do anything. So a priori, from our elementary QFT courses, we might expect that this term is completely irrelevant. Well, so at low energy, we included it by this term. So these A and B's are order 1 coefficients. And so now we're going to plug this expression for the fields in the energy Lagrangian, see what are the predictions, and compare them to experiment. So experiment is going to tell us if this term is there or not. Okay? And it's going to tell us in a very simple way, because if we plug this U right here, what we're going to get is the following. So if you remember, you can write the determinant as E of the trace of the log, but, well, the trace of the polymatrices are all 0. So if you work out the algebra, you're going to find that this term is just eta and nothing else. There is also an Hermitian conjugate. So if you want the potential of eta as a term that looks like this. Okay, and so you can expand the cosine as usual, and if you do it, this is going to predict for you that the mass of eta should be close to this dynamical scale lambda squared. Okay, and this is so this is the prediction of this low energy Lagrangian, where we included explicitly U1A breaking. Now, okay, we can see what happens to the other particles. So first of all, we can neglect the mixing between eta and the pions coming from this term, because this term scales like a quark mass matrix times the QCD scale cube, while this term scales like the QCD scale to the 4th. The QCD scale is much bigger than the 2 quark mass matrices that we have in the theory. So the potential of eta is dominated by this term that wants to set its VEV to 0. So barring corrections of order m up, m down over lambda QCD, which is a very small parameter, we can very simply compute the potential for the pions by setting eta to its VEV into this term. Okay, so this term doesn't give any contribution to the pion, and in this one we can neglect the mixing with eta for this reason. So So now all we have to do, well, which is actually quite a bit of work, is to see how that potential looks like. So now we have this trace of m times e to the I and modulo those small corrections that I've just mentioned, this is going to be the potential of the pions. So what you want to do is the usual exercise. So you want to find the minimum. If the pions have a web and that minimum, expand the potential around the web, see what the masses are, etc., etc. But OK, you already know that QCD is not breaking charge conservation. So the charged pion are going to have web 0. The neutral one might, in principle, have a web. And I'm calling the charged pions, as usual, those that are associated to this combination of the Pauli matrices. And, well, I leave to you as a rather involved algebraic exercise to show that the neutral pion indeed has a web, which is given by this expression. And that if you expand the potential around this web, you're going to get the following expression. For the neutral pion, okay? We're not going to write it down for the charged pions as well. And the mass of this guy is nothing but, so the mass squared of this guy is nothing but this. Okay, so sorry for this boring intermezzo where I just wrote down stuff. So what's the point? What's the point of this result? So the first thing we see is that this theta bar parameter that breaks CP has an effect at low energy if all the quark masses are different from 0. As you can see, it always appears multiplied by all the quark masses in the low energy theory. So if even one is 0, you don't get any result. Sorry, you don't get any effect. Second of all, well, now we have a very concrete and relatively simple to test experimental prediction that is telling us whether that GG dual term in the high energy theory had any effect or not, because we predicted that the eta meson has a mass of order lambda QCD, while the pions have a much smaller mass of order square root of lambda QCD times the mass of the up or down quark. So if we can detect these particles and measure a big hierarchy of masses, we are forced to turn on this term in the chiral Lagrangian, which corresponds to the U1A violation in the high energy theory by GG dual. And indeed, the experiment tells us that this is the case, that the eta meson is much heavier than the pions. And so now, well, we are left with a few questions to answer. The first one is, well, how can a total derivative give us an observable effect? Even worse, actually, if you compute the Hamiltonian from that Lagrangian, you'll see that theta doesn't appear at all in the Hamiltonian, but we've just worked out that it has an effect. So this is the first mystery that we need to solve. Secondly, well, if we just accept these results as fact of nature and stop questioning total derivatives, we still have another, let's say, more pragmatic question to ask, which is whether this is the best way to measure theta bar. So already from here, you see that theta bar cannot be that big because we know that the masses of the charged and neutral pions are very close to each other. But OK, maybe there is a much better way to measure theta bar, and indeed there is. So what we're going to do next is I'm going to tell you how to measure theta bar, what's the value, and I will sketch very quickly possible explanation as of why theta bar is small. As we anticipated, it is small, and it's weird that it's small. And finally, after that, I'm also going to answer the total derivative puzzle. But first, OK, if you have more questions, this is a good time to ask. You already asked a lot, so okay, I'll move forward. So, OK, let's first answer the simpler observational question. So indeed, from the pion masses, you can get a pretty decent determination of theta, which then, as a consequence, enters all sorts of quantity in hadronic physics, the binding energy of nuclei, a bunch of other stuff. But the cleanest and most precise observable that we have that is sensitive to theta is the neutron electric dipole moment. So in particular, we can write down this operator. And if you take the non-relativistic limit of this operator, you're going to find a neutron electric dipole moment proportional to this coefficient d. And you can compute d as a function of theta. And the answer is this. So if you want, I can tell you how the computation is done. It's done, well, I mean, you can get a pretty decent estimate with relatively small errors directly from the chiral Lagrangian. So if to this you add the corresponding couplings of nucleons, again, that you write down purely based on symmetry, and then measure them, you can do a one-loop calculation with a pion and a photon, here the nucleons, and you're going to get this result. Actually, there is a beautiful paper by Witten, Di Vecchia, Veneziano, and Kruter, where they do this stuff from scratch. So they also explain to you how to choose the right vacuum in such a way that there's no tadpole for the pions, et cetera, et cetera. Here we kind of did it all implicitly, leaving the algebra as an exercise. But in this paper, you're going to see all the steps, including those that from this Lagrangian plus the nucleon Lagrangian give you this result. So, well, if we have time, maybe at the end I will do the calculation for you. But for now, you can just trust the result. And then experimentally, one sees that theta bar is smaller than 10 to the minus 10. So this object is measured very precisely. And, well, as we were saying at the beginning, this is strange because theta bar is not a property that is purely confined to the QCD sector. So theta bar is a sum of theta and the phase of the determinant of the quark mass matrices. So if there are effects that break Cp at order 1 and talk to the quarks, there is no reason a priori why this object should be so small, unless, well, something non-trivial is going on in the high energy theory. Okay? Possible explanations for this fact are, well, that one quark mass is 0, so maybe a map is 0. This would solve all our problems because immediately theta bar would decouple from all observables, including this one. So I didn't write it explicitly, but also here there is a determinant of the quark mass matrices. Unfortunately, this is incompatible with lattice results. You can otherwise impose parity or Cp conservation in your high energy theory in ways that I'm not going to discuss in detail, but if you want, I can give you some references. So essentially, this is telling you that you cannot extend, so this low energy observation is telling you that you cannot extend the standard model in the most naive way possible, but that maybe your high energy theory is more symmetric than you thought. So in some sense, all fine-tuning problems end up pointing to this as a possible answer. Because really, fine-tuning problems are, well, so when they persist, they become failures of symmetry. But initially, they are only indication that the UV is not as trivial as you were imagining. Finally, okay, these two are both interesting possibilities, but we're not going to discuss them here for lack of time, mainly. Finally, well, there is the axion, okay, that many of you might have seen. So essentially, the idea is that at some high scale, let me call it Fa, there is some symmetry. The simplest one that everyone thinks about normally is this U1 Peccei-Quinn. So for instance, you can imagine that your Lagrangian at high energy contains, for instance, a term like this one, where these Q's are both left-handed spinors. So now I'm using a slightly different notation compared to the rest of the lecture. And if you assign, say, charge -2 to this guy, 1 to this guy, and 1 to this guy, this U1 effectively is an axial symmetry in the same way that we've seen before. And if these two fermions are charged under Qcd, this symmetry is anomalous, meaning that, well, it's incompatible with the gauge symmetry of Qcd. Well, you would need an entire set of lecture to talk about anomalies properly. Let me just say that if this was the case, you would generate a coupling of the Goldstone boson of this symmetry, assuming that this symmetry is spontaneously broken. So let's say that this field phi gets a VEV due to some dynamics, so some VEV Fa. Then there is a Goldstone boson associated to this PQ symmetry. And the fact that this PQ symmetry is anomalous under Qcd means that it's explicitly broken by Qcd, essentially. And so this Goldstone boson, you expect it to have a contribution to its potential from strong interactions. And in practice, you can show that in this case, your low energy Lagrangian is going to contain a term like this. If Qcd is the only source of breaking of this U1 symmetry, this is also the only source of potential for this Goldstone boson. So you can repeat exactly as we did before the Qcd Lagrangian, and then the expansion over the pions, etc., and at low energy, you're going to get a potential for this Goldstone boson and the pions, which is exactly the same as this one, only you replace theta bar with theta bar plus A over Fa. Okay? Well, it's obvious that if you started with that Lagrangian, you would have gotten exactly the same result with theta bar replaced by A over Fa. And so this happens everywhere where we have a theta bar in the low energy theory. So everywhere in the low energy theory where before there was a theta bar, now there is a theta bar plus A over Fa. And so you can ask what's the, if A has a vacuum expectation value from that potential. And indeed, it has. So what minimizes this potential is if theta bar is 0. Okay? In the theory without the axion, theta bar was just a number, so we couldn't change it to minimize the potential. But in the theory with the axion, theta bar has a field component. So the minimum of this potential is when this object is 0. And since this object is the one that appears in all observables, we've seen how to neutralize the effect of this CP violation. So this is, on paper, a very simple and economical way to explain why the neutron electric dipole moment is so small. Of course, okay, by now you should have learned that there is always a catch, and we will see it tomorrow. Before that, well, if I have some time left, I'm going to tell you the resolution of the puzzle of the total derivative. I do? Okay. What, sorry? 2 minutes. Minus, okay, then I'm going to do it tomorrow because, I mean, no, it's too much. I mean, I cannot do all the instanton stuff in minus 5 minutes. So yeah, we're gonna do the instantons tomorrow. But okay, well, let me just say, so because this part of the lectures clearly seems disconnected from what we said before, but we will see at the end that this object, other than explaining this puzzle, can also be dark matter. So we will see it tomorrow. And if we have time, we're going to see that, in principle, well, you partially have already seen it with Gilad, and that it can play a role for the hierarchy problem. So thanks.
Quick questions.
Yes.
We also have discussion.
I should.